Hello my dear students. Yes, in the previous class we discussed about the expression of the torque acting on the current loop which is placed in a uniform magnetic field. There you got one word called magnetic dipole moment. That M is nothing but I into A, which you have learnt. Fine. So previously also I discussed about what exactly the magnetic dipole moment means. In the today's class we are discussing about. So today we will study what will be the magnetic dipole moment of an electron while it is revolving in a orbit of an atom. So today we will get a expression for magnetic dipole moment of an electron while it is revolving in an atom. So this is how I have considered the diagram. Here the electrons is revolving in the orbit. So, how the electrons is moving? The electrons is moving in a circular orbit. In the previous class, we have studied that the magnetic field is produced around the circular loop when the current is passed through it. Now, which is making the current to produce? The electrons is moving. When electrons is moving, it means that your current is moving, correct? Current is passing. Electrons is moving, it means that the current is passing through that. When the current is passing through that, means there is a magnetic field is produced around that orbit. Even whatever the theory you studied in the circular loop, same thing it is applicable in your circular orbit. Now I am considering the blue line. What is the blue line? That is nothing but an electron is revolving around the circular loop. When the electrons is revolving around the circular loop, there is a magnetic field is created. So when I see like the current is passing clockwise direction, so from the above when I see, it will be south pole. Okay, I'll be seeing from the up, so it will be the south pole. When I am seeing it is an anti-clockwise direction downwards, so it is different up and down, right? When I am seeing downwards, it will be anti-clockwise, then it is north pole. Okay, we know that current is passing. Now let us consider the area of it, because for magnetic dipole I require the current. See, I is nothing but the current passing through that circular loop, or even I can say orbit. Now whatever I am shading, the shading part is nothing but an area, correct? Current is important and area is important. These are the two terms which represents your magnetic dipole. Okay, we have defined the area and current. So I will get the magnetic dipole. Now, how will be your magnetic field lines? We know that magnetic field is represented using magnetic field lines, right? So when the current in the loop flowing clockwise, it gives you the south pole. When the current in the anti-clockwise, it gives you the north pole. We know that the magnetic dipole moment is equals to the current passing through your orbit. Here we are considering an orbit, or usually when I am writing, I will write it as a circular loop, right? So the current is passing in the circular loop, that I will write. So I, where I into A, correct? The formula of magnetic dipole moment is I into A. And you know what is an area? Area is a vector quantity. Which direction your area will be there? Same direction will be your magnetic dipole moment. Yesterday only we studied again clearly, correct? So A is your vector quantity, okay, and M is also your vector quantity. I am not writing I in a vector. You know that. What is the reason? Because I is not a vector quantity. M is a vector quantity and your A is a vector quantity. So this is how I will write for magnetic dipole moment of one orbit. If there is a n number of turns, if it is 2 I will write 2, if it is 3 I will write 3, if it is having n number of turns, so what I should write? I should put n here. So n represents n number of turns. I represents, in this I represents the current and A represents the area of the circular loop. Okay, so now let us do for our electrons. Now, while I am considering an electron, let us write a orbit here. I am not considering the nucleus because I want to identify the magnetic dipole of the electron. Okay, so I am not writing any of the nucleus here. I am considering an electron. Electron will be revolving around this orbit. Okay, so let me write the electron. Electron is nothing but which charge? Electrons is a negative charge. Is it or not? So in the place of electron, E is nothing but a negative charge. Here is your electron. See, I am placing with a yellow point where that is nothing but your electron, which is negatively charged. Okay. So that is negatively charged minus E. That is equals to what? That is equals to minus 1. What is the value of the electron? I am writing minus 1.6 into 10 to the power of minus 19. So this is what the value of it. So why we are representing negative? Because electron is a negatively charged particle. And the electrons is revolving. So what I need to do here? Electrons is revolving means it is giving the magnetic field. Due to that, I need to around the electrons there is a magnetic field created. By that it is clear that I need to identify the magnetic dipole moment. Okay, how we can identify the magnetic dipole? I need to identify, correct? First I need to identify the I, then I need to identify what is the area. When I identify the I and A, I can easily identify what is the magnetic dipole moment of an electron, correct? So my job to identify your current and your area. First let us do that. Okay, we came to know that we need to identify I and A. But how? So before that, you want to know like how I need to find the I. I is nothing but Q by T. So I make something radius for the orbit. Okay. So which helps to find. Okay. First I will draw the radius to the circular orbit. Okay. The electrons will revolve one revolution. What is the time taken? Okay. Next I will take the word that is nothing but time period, because I want the time period. That is also important. I is equals to Q by T, correct? The electron to revolute one to complete one revolution, what is the time period taken? If I know the time period, I can easily identify the frequency. Correct? What is the frequency? How many number of times the revolution is taken place? Okay. This I am going to represent it by mu. So frequency I will represent by mu, and we know the formula for the frequency. Frequency is equals to 1 by T. Okay. So let us understand this clearly. So let me take the revolution is taking for the time of second. Okay. The time period which is taken by the electron is of second. In of second, how many number of times did the electrons is revoluted? Let me check it. Okay. Frequency is nothing but what? How many number of times? Frequency becomes 2 because 1 by 2 it's a reciprocal of it, right? V is equals to 1 by T, so frequency becomes 2. So this becomes what? 1 by 2, so that is a reciprocal of it. So how many number of times electrons is revoluted? 2 times. That is or 2 per second or 2 hertz. Okay. So if I am written 3 there, okay, this becomes how many number of times? In 1 by 3 seconds, the number of times the revolution has happened is 3 hertz. 3 hertz. Like this, I will relate the time period and the frequency for our understanding. Okay, this is what the frequency and that is what the time period, how it is related. Now, let us come to the derivation part, which is very important. Let us concentrate now. Now, I want I. How to identify the I in a circular loop? So let me consider first a cross-sectional area. Okay, in this particular circular orbit, let me consider one cross-sectional area which you can see in the diagram. What happens? How many number of charge which is passing through this particular cross-sectional area? That is nothing but your current. I see the cross sectional area there. I is nothing but what? The charge crossing or crossed in a 1 second. In 1 second. In 1 second, how many number of charges is passing through that? Then I can say it as, see, 1 coulomb of charges passing in 1 second, then it is said as 1 ampere of the current. Correct? No? When I am considering the cross-sectional area, see here you can see the minus 16 into 10 to the power of minus 19 electron is passing through that. Okay, 1 electron is passing through that cross-sectional area. What will be your current? Okay, so remember that if the electron is moving clockwise or it is an anti-clockwise direction, current is not at all considered. Okay, in this way, if I am taking the electron is flowing, that is a minus 1.6. If it is moving in the opposite way also, like this way, if it is moving also, that is minus 1.6. The current is a scalar quantity. It never depends on that negative at all. Okay, so that negative implies it's a negative charge. Okay, that is minus 1.6. It's 10 to the power of minus 19. Fine. Now when I am considering a current, okay, the electron which is passing through that is 1.6 into 10 to the power of minus 19. In that particular cross-sectional area, when the electrons is passing, okay, that is nothing but I is equals to Q by T. In the place of Q, I have, electron. The electrons is passing through that cross-sectional area. When the electron is passing through that cross-sectional area, I can write I is equals to Q by T. In the place of Q, I can write it as what? 1 by T is already there. That is nothing but your frequency. Or even you can represent with respect to time period, not at all a problem. So current I is equals to E divided by T, or with respect to what? E, the electron is how many number of times it's revolving, or I can say with respect to frequency also. Okay, E by T gives you the current. I hope so it is clear. This electrons is moving with some velocity, right? So let us take V. V is the velocity of the electron. Let us consider the electron is moving in a circular orbit, right? With the speed V. Okay, the V is representing the speed of it. When I am considering the speed, it is covering the distance, is it or not? Initially it is at one point, the electron is revolving. How much it is covering the distance? C is equals to 2 pi r. This is what your distance covered with your speed V. Okay, we know the formula very well about the speed. Speed is equals to distance divided by time taken. Means, now if I want time period, because here the time period refers a revolution of one electron. What is the time taken for the revolution of the electron is nothing but time period. Here what I am taking the speed. Speed is nothing but the speed of the electron while revoluting, and the distance covered is nothing but it is covering circular path. Therefore the circumference I am writing 2 pi r. So how to write the time period or how to write the t? Initially whatever the formula you know. See here how it is revolving. So the electron will come and it will move. Because it is moving in a circular path itself, I am taking your distance as c is equals to 2 pi r. When I know distance, when I know speed, I can find the time period. Now let us write the expression for the time period by using your circumference, that is nothing but the distance travelled and the speed. Okay, that is time period is equals to the distance travelled. Okay, I represent it by the capital T. The distance travelled is nothing but 2 pi r. Okay, time period where distance travelled is 2 pi r divided by speed. V represents your speed. This is what the expression for my time period. When I know okay, let me write, this is the equation 1. Okay, I is equals to E of 1 by T and T is equals to 2 pi R by V. Let us substitute this T value in my equation number 1. What is the T value? Okay, let us substitute that in your equation 1. Now let us substitute. Okay, T is equals to 2 pi R by V. I is equals to E into, in the place of the reciprocal of the T, I am writing first 2 pi R, okay, by V. It goes to where? To your numerator. That let us do in the next step, 2 pi R divided by V. This becomes E, that V will go up, so E into V divided by 2 pi R. 2 pi R. This is what my I term. Okay, in magnetic dipole I got the I value. Let me take that as equation number 3. In magnetic dipole I got I. So next what I need to, so this I value, let us substitute there. Okay, that is I is equals to E V divided by 2 pi R. Okay, see here, area is nothing but what? It's a circular path. See the yellow line? It's a circular, right? What is the area of this circle? We all know what is the area of the circle, right? What is the area of the circle? Let me write. A is equals to area of the circle is equals to pi R square. So I got I term also, I got your area also. Now let us substitute in the magnetic dipole moment, that is I value. Okay, in this let us substitute that values. Okay, so let me write it. What is your I value? So equation number 3 we have. Now let me write it, that is EV divided by 2 pi R into what is my area? Area is nothing but pi R square. Let me cancel out pi and R. So what you will be getting? EV R, okay, divided by 2. Correct? This is what my magnetic dipole. But still we can simplify this. Okay, let us write this equation as number 4. Okay, this is what my equation number 4. Now let me write, or let me simplify. Okay, let me continue this. You can continue. I have made a line over here. Okay, because of the next step I have written a line here. Okay, where M I got EVR divided by 2. Now let us write like this, that is L is equals to, L is nothing but angular momentum. I hope so you studied in your first PUC, is it or not? L is nothing but angular momentum. Angular momentum formula is ME, means a mass of an electron. Here I need to consider mass of the electron, not just M, okay, because the electron is revolving. Mass of the electron V, okay, M into VR. Okay, VR is nothing but velocity into radius of that particular orbit. So angular momentum formula is MVR. Now this magnetic dipole moment, I have VR here, you can see, right? VR here. Now I will take this expression. Okay, I will take VR now. I want only VR. So what happens? Your L divided by ME it becomes. If I want only VR, it becomes like this. That is L divided by ME. Okay. Now this value, that is VR value, is equals to what? L divided by ME. This value, let me substitute in this place VR. Okay, let me substitute in the place of VR. Now let us write. Okay, when I am writing in the place of VR, what I am writing? In the place of VR I am writing M is equals to E is as usual. You can write the E there. Okay, in the place of E I am writing E itself. In the place of VR, I am considering L divided by ME. L divided by ME. Down you have 2 also. Therefore 2ME. okay, 2me. This is what my expression for magnetic dipole moment of revolving electron. But still, see here, E is constant and 2 is constant. Me is also constant, right? Now L by Me, I just substituted the value over here. I just, in the place of Vr, I have written L by Me, okay, where E is constant, 2 is constant, Me is constant. But you remember, magnetic dipole moment, it's a vector quantity. Even here one term should be a vector quantity, right? E is constant, 2 is constant, Me is constant, and which is a vector quantity. Okay, so I represented a magnetic dipole. I got the equation, everything, but this is a magnitude. I got only magnitude. With respect to direction also, I need to write it. Okay, it's in a vector form. With respect to direction means what? It's a vector form. How to write the vector notation? Now let us write in the vector notation, that is m vector, okay, is equals to E is a constant divided by EL divided by 2ME. So when I said E is constant, ME is constant, 2 is constant, which is the remaining one? E is constant, ME is constant, 2 obviously constant. So L is the vector 1, okay. So this L becomes the vector, okay. Let us consider the direction of the L, okay. L is a vector. Let us see the diagram now. Now let us consider the rotation in this way, okay. So the electron is revolving in this particular direction. Obviously it creates some angular momentum. There will be some momentum when it is having the mass and velocity. Now this is what the direction of your angular momentum, that is nothing but L. When I am considering the magnetic field, it is opposite to your angular momentum, okay. So when I am considering the magnetic field direction, it is opposite to your angular momentum. Where will be your magnetic field? Same direction will be your magnetic dipole moment, okay. So both are opposite to each other, your angular momentum and your magnetic dipole moment, both are opposite to each other. Therefore I am representing the negative sign, okay. Therefore I am representing the negative sign. Why I am representing the negative sign? Because both are opposite to each other. So this is what the expression for it. Thank you all. Have a nice day. Practice well.